Today we're going to begin talking about electric circuits involving current. Before we start with current, let's make sure we understand what takes place within electrostatics and the difference between electrostatics and electricity. When we talk about an idea of electrostatics, we're looking at the concept of charges on objects that are not moving. And I think that's the key point here to make sure we get. Objects can have either positive or negative charge, right? Like charges repel and opposites attract. And a force is generated or created between the charges. And that's where we apply the concept of Coulomb's law. That Q1, charge of one object, along with the charge of the other two, is going to determine if it's either repelling or attracting. And then we have the most important feature here of distance. So in this case, we're talking about the electric force is equal to K, this constant value, between two whatever the charges are, either positive or negative, at some distance. And even tiny amounts of charge can generate tremendous forces. As you can see, the constant here is very, very large, 9 times 10 to the 9th Newton meter squared per Coulomb squared. Here's a picture of polarization of how the negatively charged balloon repels the electrons, creating a slightly temporary positively charged wall which allows the balloon to stick, just due to electrostatic forces. Here I have a negative charge of the balloon, I have a positive charge of the wall. They're very, very close together. It's enough to create an electric force that's significantly greater than that of gravity. And then lastly, the three ways to charge an object. We can charge by friction, right? This is how we charge the balloon here in the picture on the right. We can charge by contact, where we directly transfer, and we can charge by induction. When we talk about electric current, I think it's important that you realize that we're always using electricity, that we are dependent on electricity in current, that we just plug something in or we use batteries. So both of which are important and significant in our world, but they are different to each other. When I use batteries, I'm using direct current. When I plug something into a wall, I'm using alternating current, two different forms of electricity. Here's electric circuits. We're going to be looking at circuit diagrams and symbols here soon, but essentially we're going to be comparing a circuit of water. How water kind of is distributed through the house is very similar to that of electric circuits. And here's a circuit, this is kind of an example from the textbook, and here's a circuit symbol. Circuit diagram using symbols. Notice that this is an open circuit, so this bulb, if this is indicating this, is incorrect. This is both, this bulb would not be on, but this one here shows it is. So this open circuit would not allow for it. And then secondly, you can see the cathode is here and the electrode is over here. The cathode here and the anode is over here. So be careful here, because I think there's two errors on this picture. Circuit diagrams involve wires, cathode, anode. We've got different resistors. In this case, it's a bulb. We've got different resistors that control the amount of current. And lastly, a switch. A switch kind of opens and closes a circuit. And here we're just going to get some practice talking about how 1.5 volts provides current. Here I just have a switch in here. And these bulbs light up if I have current flowing. And it's that simple. When we talk about open and closed, it's important to realize that if it's an open switch, the switch, it does not allow for current to flow, and if I close that switch, current can flow. Notice that we're now going to start defining current as traveling or flowing from cathode to anode, and we will differentiate between how electrons move, which is actually anode to cathode. So what is current? So current is the movement of electric charge, or the flow of charge. Current flows when free-flowing electrons move, and current is measured in amperes, or amps, we'll call capital A. And here we can identify the picture here. Current is flowing cathode to anode. And now make sure you realize that electrons are identified as flowing from the anode to cathode. So why does current flow? Well, just as there is a difference in energy between 2 points from, say, dropping a ball from, off the ground to the ball being resting on the ground, there's different amounts of energy. Right? So water flows downhill from high gravitational potential energy to low gravitational potential energy. Well, current flows from high electric PE to low electrical PE. So from high to low. So we've created this difference that's always going to flow the equivalent of downhill. If I consider Niagara Falls, gravitational potential energy to low potential energy, at the top it has high potential energy, at the bottom it has low potential energy. So essentially, we've got an analogy that's similar to what's taking place within a battery. So what is voltage? Well, voltage is the difference in electrical PE between 2 points in a circuit. And here it's important to realize that voltage is measured in volts, or capital V, and the difference of voltage is required for current to flow. It's literally going to be pushing current through a wire. It's going to be pushed from a high to low electric potential energy. And be sure to read this passage here. We're comparing the Middle Fork River to Niagara Falls. Niagara Falls has a very, very steep drop, where the Middle Fork River has a very, very tiny drop in its flow. Here we can see there's no height difference, so no current, there's no potential difference. Here I've got some amount of potential difference, so therefore this is the equivalent of current flowing. Current versus electron flow, just a recap of current flows from cathode to anode, and electrons move from anode to cathode. This is just two different ways of viewing conventional versus the modern electron flow. Two different ways to describe what's taking place within a circuit, or within a circuit or wires. A voltage drop or difference in voltage, realize that current is considered to be moving from this direction. It's providing the energy to light this up, and then it's returning as it's just continuing the circulation or the movement here. What is resistance? Resistance is just kind of like, this is showing an example of if I have a very small opening for water flow out, this would be considered a high resistance, and if I have a larger opening, it's a low resistance, that this water will fall out significantly faster than here because it has a lower resistance. Take a look at single bulb, 2 bulbs, and 3 bulbs. If we keep the batteries the same, right, 1.5 volts. If I increase if I increase the light bulbs, I'm increasing resistance. I would be then decreasing current. I can see the decrease in current leading to a decrease in brightness. So we're going to be making the analogy of the greater the current, the greater the brightness. The less the current, the less the brightness, or dimmer in this case. Here's the difference between conductors and insulators. Conductors allow for electrons to move, and insulators do not allow for, they impede the ability for electrons to move. So insulators typically cover conductors, right? Our world is based on wires. Wires are very nice metals that are inside here that allow for electrons to flow, and they're covered by plastic or rubber insulators. And here's just a cross section of what's going on within the wire itself. And then here, we last but never least, wet skin versus dry skin. Dry skin is a very high resistance, so we actually don't necessarily get damaged or injured when we get zapped by something. But if we had wet skin, it lowers our resistance. Therefore, we would have a much greater current passing through your body. And as we all know, current kills.